Okay, so finishing up rational functions, we're going to look at rational equations, and this is going to relate to graphing. And there's two special cases that we're going to have to account for, two special cases that we haven't looked at specifically yet. The equations that you've been given, for the most part, have avoided these just so we kind of take care of them at the end. So our first special case is when we get holes in the graph. Okay, so it could be referred to as holes in the graph. It could be referred to as gaps in the graph. Either way, we got a little something there we have to kind of account for. And when that happens is when our denominator is going to cancel out. Okay, so we would get that in a situation where we had, say, x squared minus x minus 6 over x plus 2. Okay. From here, what are our restrictions? Okay. X can't equal -2. Okay. If we're doing a graph of this, this would be our vertical asymptote. Okay, but if we take the next step and factor our numerator, we have an x plus 2 term in both our numerator and our denominator. So we could take that and we could cancel both of them out, and we'd be left with a function x minus 3. So we say this is a linear function, and we just got to keep in mind that x can equal -2. So if we if we want to graph this linear function, well, it's a straight line, y-intercept -3. It's going to go like that, but we have to have something happen at -2. Because for all other cases, it's going to be a straight line. So what you would do in this case is you would plug in -2, because for x minus 3, it would work, right? So we could plug in -2, and we would get -2 minus 3. So we plug that into our simplified equation. We get -5. So that tells us for x minus 3, we have a point -2, -5. Okay, but we can't have that point on our line because x can't equal -2. So what we'll do is we'll draw a little circle, and we can say discontinuous. Discontinuous at the point -2, -5. Okay, so we'll do a second example here. And our second example is we're going to look at sketching the graph of 2x squared minus 7x minus 4 over 2x squared plus 5x plus 2. Okay, so what's going to be our first step in this case? Okay, so we're going to factor out the numerator and the denominator. So whatever one you want to factor first, we can. If we do that, we should find out that we're going to get 2x plus 1 and x minus 4 over 2x plus 1 and x plus 2. Okay, so we can factor both numerator and denominator into that. So looking at that equation, what do we know from this equation? Okay, so right now from here, we have our restrictions that x can equal -2 and x can equal -1/2. Okay, so before you start canceling things out, it works out well if you write out your restrictions. all of your restrictions are either going to be gaps or asymptotes. Okay? So they're going to be one of the two. Okay? And from here, we have an x or 2x plus 1 in numerator and denominator. We can cancel out both of these. So we're left with x minus 4 over x plus 2. Okay? Because we're able to cancel it, this guy is going to be our gap. And this one is our vertical asymptote. So we can start our graph from there. So we have a vertical asymptote at -2. Okay. And now we continue to graph that in the exact same way we did before. So what's our next step in graphing? Okay, so we can find our x and y intercept. How do we find our x-intercept? So x-intercept, y equals 0. So you plug it into the equation, x minus 4 over x plus 2. Multiply out the denominator. Now what's any number times 0? 0. A couple people had any number times 0 as being 1, so they'd just move the x plus 2 over. So we're going to have 0 equals x minus 4. So x equals 4. We have a point at 4 and 0. So we can go over, we can put that point 4 and 0. From there we can find our y-intercept. Y-intercept, x equals 0. So -4 over 2. -2. So we have a point at 0, -2, which we can put down here. And the scale on my graph is probably going to be a little off, but we get the idea. Now, just based on these 2 points, what should we expect to happen? So once we get the x and y intercept, we plot them on our graph, and just based on what we know about how these graphs behave, we should be able to figure out that our end behavior is going to be positive, and as we approach our vertical asymptote from the right, it should be heading towards -infinity. So we can do those. Those are a nice little check just to make sure, all right, well, what I'm getting is going to make sense. So let's see what actually happens when x approaches -2 from the right. So if we look at our function, we have x minus 4 over x plus 2. What are we going to get in our numerator if we're looking at just in terms of the sign of our function? A negative term in our numerator, in our denominator, positive. So we're looking at a -1.99 plus 2. It's going to be positive. So this is going to -infinity. So we're on the right track. Let's look at when it approaches -2 from the left. So something a little bit more negative. So say -2.01. We're still going to get that negative term in our numerator. We'll get a negative term in our denominator. So this function is going to approach positive infinity from the left-hand side, which makes sense. We've got it up here. Now all that's left is to figure out where the horizontal asymptote is going to go. So how do we figure out that? Factor out an x from our function. So if we look at I'll just change that from an F to a G. So if we look at that, we factor out an x from our equation. So x 1 minus 4 over x, x 1 plus 2 over x. And then you're going to be left with so we can use this form of our function to evaluate it when x approaches positive infinity and when x approaches negative infinity. In both cases, you're going to get the second term in both the numerator and denominator going to 0. And we're just going to be left with 1, which is going to be our horizontal asymptote, which is a positive number, which was what we kind of expected. And we can go back up here, put in our horizontal asymptote at 1, and finish our graph. So now we got to go back up. We have our graph pretty well finished. Let's go back up to our graph. All right, we accounted for our vertical asymptote. Now we just got to account for our gap. So our gap happens when x equals -0.5, okay, which is going to be somewhere in here. So our gap is going to be right in there. So if we go back to our simplified version of our function, and let's see what happens at -1/2, -1/2 minus 4 over -1/2 plus 2. So we're going to have -4.5 in our numerator and 1.5 in our denominator. So if we work that out, so -4.5 divided by 1.5 is, so work out that it's -3. So if we didn't have a gap, we would have the point -1/2 and -3. But because that canceled out here, we have our gap. So our graph is going to be discontinuous, or we're going to have a gap at -1/2 and -3. Okay, so the second special case we're going to look at is what we call a slant asymptote or an oblique asymptote. Okay, so it's going to be an asymptote, but it's not going to be vertical or it's not going to be horizontal. It's going to be a slant. It's going to be on a slant. So an asymptote okay. So an asymptote that is on a slant. Okay. It's going to happen when the degree of the numerator is 1 more than the degree of the denominator. Okay. So if we do an example of this, we're looking at obtaining the graph for the function x squared minus 2x minus 5 over x minus 1. So in this case, our numerator has degree 2, our denominator has degree 1. So that's 1 more. So this will have an oblique asymptote. Okay, and we know that just based on looking at it and looking at the degrees. Okay, so let's start graphing this, and let's forget about the oblique asymptote for now. Let's start graphing this how we normally would. So what would we do first? So if we're looking at graphing this equation, the first thing we would look at, all right, can we factor our numerator? We can't factor that, so we're going to have to leave it as is. That's not going to change anything. The only thing that's going to make it a little bit more difficult to do is to find our x-intercepts. Okay, but other than that, we can still continue on. So if we look at this, we have, what's our restriction here? Okay, so we have a restriction. X can't equal +1. So if we start our graph, +1, we have a vertical asymptote. We could start off with saying, all right, well, next thing we can do, let's find our y-intercept. And that happens when x is 0. 0 minus 2 times 0 minus 5 over 0 minus 1. So we get a point of +5 for our y-intercept. We could look at finding our x-intercepts. That means y equals 0. So we're going to left with 0 equals x squared minus 2x minus 5 over x minus 1. Multiplying both sides by x minus 1, we have 0 equals x squared minus 2x minus 5. We can't factor that. If we're able to factor it, it would have been a little bit nicer. So what we're going to have to do is use the quadratic formula. Okay, so we can use the quadratic formula. We're not going to spend a bunch of time to go through that. And we get solutions 1 plus or minus root x. So that's going to give us 2 points, 3.45 and 0, and negative 1.45 and 0. So we go back up to our graph, and we can put those in. So next is to figure out how our graph behaves around our asymptotes. So we're looking at how x approaches 1 from the left and how x approaches 1 from the right. Again, if we go back up to our graph and just kind of use what we have already done, we should expect to see it approach 1 from the left be positive infinity. And you're probably going to guess that from as it approaches 1 from the right, it's going to be down here. But we have to prove that. So let's go down. We're plugging in 1 from the left. And what are we going to get? Negative. So if we're approaching -1 from the left, we have a minus 2x minus 5. You can expect the top term to be negative. And say 1 from the left would be like 0.99. So at 0.99 minus 1, you're going to have a negative in the denominator. So we're going to get positive infinity. And the same idea, we're going to have a negative in the numerator, but a positive in the denominator. So from the right, it's going to approach negative infinity. So that's kind of what we expected to happen, which is good. So now we have to deal with the end behavior. And the end behavior is going to be where we have to talk about a slant asymptote. So what happens with a slant asymptote is, well, we're trying to evaluate the function x squared minus 2x minus 5 over x minus 1. This is just a division statement. Okay, so if we did long division on this division statement, okay, and this one's actually a bit easier to do long division on as opposed to synthetic. The reason being is that we're going to be having a remainder. So if we do long division on this, okay, we're going to get, well, we're going to put in x. X times x is going to give us x squared. X times -1 is going to give us negative 1x. You can put that in. We're going to subtract the whole thing. -2 subtract -1x is going to give us -x. We bring down the 5, and we have times -1. So we do long division on this polynomial. We have our quotient up here. We have our remainder. And from this, we can jump back in time to when we did long division. And we could write that as a division statement. We could say that x squared minus 2x minus 5 over x minus 1 equals x minus 1 plus -6 over x minus 1. So we're going to use this division statement, and we're going to use this to find out our end behavior. We're going to use this to determine our end behavior. So how we use that is we say, all right, we're going to take this division statement, and let's see what happens when x approaches infinity, when x gets really, really big. Well, what's going to happen in that division statement is that this last term starts being worth less and less. It starts going away. It starts approaching 0. And all we're going to be left with is this part. Okay, this is going to be the equation that's going to represent our slant asymptote. Because what happens as our function gets really big, that second part, or as x gets really big, that second part of our function goes away, and our function is going to approach x minus 1. And the same thing happens when we go when x goes really small. Our function is going to approach x minus 1. So x minus 1 is going to be our slant asymptote. So how we deal with that, we go back up to our graph. We say, all right, well, if we're going to graph x minus 1, our slant asymptote, we would graph that. That would be a line that went something like this. Let's change that. So that's going to be our slant asymptote. Let's call it slant of x equals x minus 1. Okay, and now we know that as our graph approaches infinity or approaches negative infinity, it's going to get really close to this oblique asymptote. So if we're drawing the left side of it, it's going to come down, go through our x-intercepts, through our y-intercepts, and approach that line. And the same thing heading this way.